All right, so get this. Today we're diving into quadratic forms. We've got looks like some lecture notes here on constrained extrema of quadratic forms. Sounds kind of, I don't know, intimidating when you say it like that.
Yeah, it's definitely a mouthful, but honestly, it's a really fascinating area of math.
Yeah.
Basically, we're trying to figure out how do you find the highest point and the lowest point of these, well, these special kind of mathematical expressions when you've got, variables like x and y that are kind of stuck in a certain area, like let's say a circle.
Okay, yeah, I think I'm with you. And right away I see this example, 2x that's up plus 6y plus 2y on. So what is it about this that like makes it a quadratic form?
So it's all about those square terms you see in there. The x, the y, even that x-th term. They combine in this, well, this specific way to make what we call a quadratic expression with two variables. You'll see other examples like 10x sap plus 6 biddies plus 2y dridie to show how these things work.
Gotcha. So it's about how x and I relate to each other in the expression.
Okay.
And then the lecture, it kind of jumps right into this big question. How do we actually find those maximum and minimum values when the x and y, they're constrained? Specifically, they have to stay on a unit circle, which, just to remind myself, unit circle means radius of 1, right?
Yeah. Exactly, radius of 1. And if you try to picture it, visually, this quadratic form, it could be, well, it could be a lot of different curves depending on what x and y are doing. But by saying, hey, those x and y values, they got to stay on that unit circle, it's like asking, where on this circle does our quadratic form reach its highest and lowest points?
So we've got this circle. I know it's like we're trying to see where this quadratic form, whatever it ends up looking like, where it kind of hits its peaks and valleys, but only along that circle's path, right?
Yeah, that's a really good way to think about it. And what's really cool is that this whole thing, finding these max and min values, it's like deeply tied into understanding shapes, like ellipses, hyperbolas, that kind of thing.
Okay, now that's what I'm talking about. This is where it gets really interesting. So the lecture, it dives into a specific example. This quadratic form, 10xi plus 6i plus 2yz, and we're figuring out its max and min on the unit circle. And I gotta say, I love a good shortcut. They actually give us the answers right up front. Max is 11, minimum's 1.
And sometimes, knowing the answer beforehand, it lets us focus more on the how and the why of the solution, which is a lot of times way more interesting than just the answer by itself.
Totally agree. So they walk us through proving that those are actually the max and min, and they use, get this, completing the square. Always feels like a magic trick when I pull that one off.
It's a really powerful tool. Completing the square really lets us show super clearly that, yeah, 11 and 1, those are our max and min values for that quadratic form. As long as, of course, our x and y, they're stuck on that unit circle.
Okay, so we've got the algebra side of things, but then the lecture, it takes this awesome turn towards like the geometric side of things.
Right, and this is where I think the real beauty of this stuff comes in, because
Yeah.
as we often find, there's a visual story kind of hidden within the equations themselves. Remember our constraint, x plus 1 plus 1. Well, hey, that's the unit circle's equation right there.
Oh, right. And then we take our quadratic form, we set it equal to 11, its max, and then again to 1, the minimum. And those equations, those give us the ellipses.
Exactly. And just like that, we've got this geometric way of seeing our solution. Imagine this. The points where our unit circle cuts through those ellipses. Those are the exact spots where the quadratic form hits its highest and lowest values.
I'm picturing it. It's like those ellipses are, I don't know, contour lines or something, and where they touch the circle, boom, that's our max and min.
Perfect analogy. This back and forth between the algebra and the geometry, it's like the heart of math,
Yeah.
finding these different ways to look at the same idea.
Now I'm all about a good coordinate transformation, like changing your point of view to get a better look. And that's what the lecture tells us to do next.
Ah, yes. And this is where things get, well, even more interesting, I'd say. Because instead of sticking with our regular x and y coordinates, the notes, they're like, hey, let's switch it up. We're introduced to u and v.
And those u and v, it's not just random, right? They come from something called the eigenvectors of a matrix. And that matrix, it's like a representation of our quadratic form.
You got it. Eigenvectors and eigenvalues, they sound kind of scary, I know. But really what they're doing is finding the directions of the most stretch and squash when a matrix acts on a vector.
Yeah.
And this specific transformation we're doing with these eigenvectors, it gives us a way simpler way to write our quadratic form. We get u plus 11v form.
Whoa, that's way simpler than before. We went from 10x var plus 6xi plus 2y bar to just u otter plus 11v form. It's like trading in, I don't know, a clunky old calculator for a brand new one.
Exactly. And just like that new calculator, this new form, it lets us solve things way easier and faster. But hold on, because it doesn't stop there. Remember our whole geometric picture from before? Well, this coordinate transformation, it's not just about making the algebra look nicer. It actually changes our picture, too. Remember that unit circle and those ellipses we had in the XY world? Well, they get kind of like mapped over to a new unit circle and new ellipses. But this time, they're hanging out in the UV plane.
So it's like we took our old graph paper and we're just looking at it through, I don't know, like one of those warped mirrors at a carnival or something. Same picture, just
Yeah,
distorted.
kind of. It's more like we're putting on a new pair of glasses.
Yeah.
And with these new UV glasses on, the max and mean of our quadratic form, they become like super obvious. They line up with specific points on the unit circle, but in this new UV space.
I love how a change in perspective can do that, just make things click. But the lecture doesn't stop at just this one example, does it? It goes on to say, hey, here's how you find the max and min for any quadratic form, like something like axaw plus 2 biaca plus psi, as long as it's still stuck on that unit circle.
Absolutely, yeah. That's where we can really see how powerful these techniques are. And to do this, the lecture brings up this thing called the characteristic equation, which is a big deal in linear algebra. And get this, the roots of this equation, we usually call them ORO and OBR, those roots directly tell us our max and min values.
Wait, hold on. So I solved this characteristic equation. I find its roots, and bam, those are the exact max and min values we've been looking for this whole time.
Yep. Pretty elegant, right? And there's even more to it. Remember how we talked about quadratic forms being related to like the shapes of curves? Well, those values, our roots, they oddly give us information about what those curves look like. Like, are they ellipses, hyperbolas, other weird curves called conic sections? The roots hold the key.
Okay, see, now you're blowing my mind a little. We started with just finding the highest and lowest points, and now we're like decoding the shapes of curves using linear algebra. It's amazing how everything's connected like that.
That's what makes math so cool. It's all about these hidden links between ideas that seem totally different on the surface.
So let me recap for a sec. We started with trying to find the max and mean of a quadratic form, but only when it's on a unit circle. Seemed tricky at first, but then
We found these really elegant ways to solve it by kind of blending together algebra, geometry, and some key ideas from linear algebra. Like, who knew switching from x and y to u and v could make such a difference, right?
right, and we can't forget about eigenvectors and eigenvalues. They were the key to finding that perfect transformation, that perfect shift in perspective. It's amazing how all these different parts of math can work together.
And speaking of different perspectives, it makes you wonder, right? Like, we've been laser focused on the unit circle as our constraint, this perfect circle that our variables can't escape. But what if we change things up a bit?
Yeah, like what if instead of a circle, it was, I don't know, a square or a triangle even, or some other funky shape and we're stuck inside that? What happens to our max and min then?
Ooh, that's a great question. Gets into even weirder, more interesting stuff. When you change that constraint, the tools we use, they might have to change too. We might still use these coordinate transformations to make things simpler, but the exact transformation, it might be different. You know what I mean?
So it's still about finding that right angle, that right perspective, but we got to kind of adjust our lens depending on the shape we're stuck with.
Yeah, exactly. We might not use eigenvectors anymore. We might have to dig into like other linear algebra tools or even calculus to find those really slick transformations that unlock the problem.
So our toolbox is still good. It's just that different problems, they call for different tools.
100%. Each constraint, it's like a whole new puzzle. And it's so cool to think about all the creative ways we can solve them. That's what math is all about to me, exploring and finding these amazing connections.
This whole deep dive has been, I don't know, it's been eye-opening. We started with this like very specific thing, max and min of a quadratic form on a unit circle. But we ended up uncovering so much more than that.
Right. We saw how all these different parts of math, algebra, geometry, linear algebra, they all work together to help us solve these puzzles. It's like getting a peek behind the curtain, seeing how everything's connected in this elegant way.
And that whole idea of changing how we look at the problem, finding that perfect coordinate transformation, that's huge. Sometimes the answer isn't about like brute forcing it. It's about finding that shift in perspective.
Exactly. And as you learn more and more math, you'll see these themes pop up again and again, transformations, connections, these really elegant solutions. It never stops being an adventure. And honestly, the more you discover, the more you realize how much more there is out there to find.
So to everyone listening, if you're ever facing like a mathematical mountain in front of you, remember this. There's always more than one way to get to the top. Don't be afraid to explore, change your view, embrace the elegance of math. You might just find something truly amazing along the way.